Section 6.2 is the conservation of momentum. The objectives are going to be to describe the motion of two objects after interactions with one another and to apply the law of conservation of momentum in order to determine the motion of the objects. Similar to the law of conservation of mechanical energy, we can say that the total momentum of all objects interacting with one another remains constant. So we're pretty much saying that the momentum of the system initially is equal to the momentum of the system at the end. And remember, this symbol, sigma here, means sum. So the sum of the momenta of all the objects initially equals the sum at the end. Now, if we have two objects colliding, we have to think about the fact that beforehand we've got both objects. So object 1 times its velocity initially. That's momentum for object 1 initially. This is the momentum for object 2 initially. Here's the momentum for object 1 at the end, and here's the momentum for object 2 at the end. So this is for two objects. And notice if we had three objects, we'd have another term on each side. We'd have an m3 v3i over here and an m3 v3f over here. Example 1. A hockey player swings his hockey stick with a mass of 1 kilogram at a hockey puck that has a mass of 125 grams. He swings the stick with a velocity of 40 meters per second, and after the collision, the stick speed is 30 meters per second, but in the same direction still. If the puck was initially at rest, what is its velocity after the collision? So, in a problem like this, we have to notice several things first of all. Right away, notice the stick speed decreases by 10 meters per second because it interacts with the hockey puck, causing it to have to accelerate the hockey puck to get it moving. So it's got to decrease in velocity. What we're also going to notice is that the velocity decrease of the stick is 10 meters per second. And we know that the stick weighs or has a higher mass than the actual puck. So that means that the puck is going to gain the momentum that the stick lost from decreasing its velocity. So it's going to gain the same amount of momentum, but since momentum is the product of mass and velocity, we know that it's going to gain velocity that's probably going to be greater than this 10. Again, think about it. A stick loses 10 meters per second in velocity. The puck is only a small object. If it's gaining the same amount of momentum that the stick lost, it's got to be gaining more than 10 meters per second in velocity simply because it's a smaller object or it has less mass. Now we can prove that mathematically. Let's list what we know. We know that the mass of the hockey stick is 1 kilogram. The mass of the puck is 0.125 kilograms. Notice these differ by a factor of 8. So the stick is 8 times as massive as the puck. And let's keep that in the back of our mind. Let's just remember that figure. Next, we know that he swings the stick with a velocity of 40 meters per second. Okay, and that's before the collision. So we could say that v1i is equal to 40 meters per second. But then we know that after the collision, the stick speed is 30 meters per second. So v1f is 30 meters per second. The puck is initially at rest, so v2i is going to be 0. And what we're looking for is the puck's velocity after the collision. So we can go back and think about our equation that we looked at a moment ago, and we could realize that v2i is 0, so we don't have to account for it. I'm going to write it out just to be safe so we can see it, but again, in the future, you don't have to actually go through this process. And again, what I'm referring to is the fact that this drops off. Okay, this goes to 0. So when you're writing out your equations of motion, you don't really need to write out the component that drops off. So we didn't have to write this here. We could have just written this, this, and this. Now, we're looking for v2f, so we're trying to solve for this variable. So let's subtract this over here. Again, this is gone. Let's subtract this over here, giving us m1 v1i minus m1 v1f equals m2 v2f. Finally, at the last step, we need to divide by m2 on both sides, canceling here, leaving us with v2f on the right side, and the answer in generic form on the left side. Now we can plug in our givens here. We have a 1 kilogram mass times an initial velocity of 40 meters per second minus a 1 kilogram mass, still the stick, times a velocity of 30 meters per second, all over 0.125. And what I want to do here is not jump right to the answer, but actually look at our numerator and denominator. The numerator just turns out to be 10, and the denominator is 0.125. And this is our V2F. So what we get as an answer here is 80. And think back to what we said before. We said that the change in velocity in the stick was 10 meters per second. And so the hockey puck should change by 10 meters per second or more because it had less mass. And it turned out that the mass of the stick being 1 and the mass of the puck being 0.125 differ by a factor of 8. So therefore, our change in velocity of the stick, which happened to be 10, is going to be 1/8 of the change in velocity of the puck, which turns out to be 80 meters per second. Again, this is the change in velocity because the initial velocity of the puck was 0. So 80 minus 0 is just 80. One soccer ball is kicked down the field and collides with another soccer ball that is at rest. Assume the soccer balls are identical. If the ball that is moving before the collision has a velocity of 12 meters per second east before it hits the other ball, and a velocity of 4 meters per second afterward, then what is the velocity of the ball that was initially at rest after the collision? So we've got one soccer ball traveling east with a velocity of 12 meters per second. We've got another soccer ball sitting here at rest with a velocity of 0 meters per second. There's then interaction. It collides, and the trailing soccer ball is still moving forward, but now it's only moving forward with a velocity of 4 meters per second. And we want to know, with what velocity does it propel this ball forward? So we can start with our equations of motion. Now, I'm not going to put anything here because V2I is 0. So I don't need to put plus M2 V2I here. It's not even significant. So I'm going to leave that alone. I'm just going to put equals. And we have M1 V1F plus M2 V2F. Now, notice, we've been giving subscripts M1 and M2, but we're not given anything about the mass. We're told that the masses are all equal. So we can simply erase our masses. We don't have to consider these subscripts anymore. The subscripts are gone. Now, if there's mass in every equation, we can divide the whole equation by m, and all of the masses end up dropping off. This mass cancels with all of these masses, as long as it's in every term. Leaving behind the result, V1I equals V1F plus V2F. This was 12, this was 4, meaning this has to be 8. And it makes sense, simply because the change in velocity of one ball was from 12 to 4, so it lost 8 meters per second, and the other ball gained all 8 meters per second because they were identical in mass. Example 3. A person with a mass of 50 kilograms jumps off of a platform with a velocity of 5 meters per second to the west. So we've got some sort of a platform here. Person is jumping off to the west. If he lands on a cart has a mass of 20 kilograms with wheels on the bottom, and that cart is initially at rest, what will their combined velocity be immediately after landing? So this person is hopping off here just to land in the cart. So once he lands in the cart and the person together are going to move in this direction. So there's going to be a person in the cart now, and they're going to be moving together. So before the collision, or before the interaction, we have the person separate here and the cart separate here. The cart isn't moving initially, so there's no initial momentum here. So we could say that, we'll call this mass 1. We'll say the person's mass is 50 kilograms, and the person's initial velocity, V1I, is 5 meters per second west. So we could say negative 5 meters per second. The cart is not moving. We know its mass. Mass is 20 kilograms, but it's got no initial velocity. So that's not going to be part of our problem. But afterward, what we need to notice is that they're combined. They're one entity. So the mass here is equal to m1 plus m2. And we are trying to find out the combined velocity, or simply Vf at the end. So let's write down our equations of motion. Before the problem begins, or before the interaction occurs, we have a person moving. So we have m1 v1I. The cart is not moving, so we could ignore that. We don't have to put plus m2 v2I, so this just equals. Well, afterward, we don't have separate parts anymore. We have one entity. one object moving, and its object's mass is m1 plus m2. Remember to put parentheses around it because it's an entity. They're one object, and they are moving at a velocity vf. There's no need to put v1f or v2f because there's only one object after the interaction occurs here. At this point in time, we're trying to find vf. We can simply divide by the quantity m1 plus m2 on both sides. And it may be useful to put parentheses here to remind you that when you put it in your calculator, you need parentheses around your denominator. Okay, but that all cancels. This, again, remember, this is like a coefficient. This is 50, this is 20, this number is actually 70 VF. Okay? So our final solution here, or our algebraic final solution here, would be just, again, m1 v1I over the quantity m1 plus m2, and that is equal to VF. If you plugged in numbers earlier on, you'd have plugged in numbers here. Okay, you'd have 50 times the velocity of negative 5. That would be negative 250, and this would be 70. So it would be negative 250 equals 70 VF. Just divide by 70. It's the same thing you get here. This becomes negative 250 over 70, giving us a result of negative 3.6 meters per second. One thing we should point out, if we take a look at the speed in this problem, the speed of the person jumping was 5 meters per second. The velocity of the person in the cart afterward is 3.6 meters per second. Notice the speed reduced. And again, I'm saying speed, not velocity, but speed. Notice the speed reduced. The absolute value, or the magnitude of the velocity, has gone down. This makes sense again because instead of just a person moving, now the person has to jump into the cart and transfer some of his momentum into the cart to get it moving. And again, therefore, the overall speed of the person in the cart as a system is less than the speed of the person initially. Example 4 says 2 ice skaters are standing together at rest in the center of the rink. They push off one another in order to move in opposite directions. If the mass of person A is 60 kilograms, the mass of person B is 40 kilograms, and the velocity of person B after pushing off is 7 meters per second, what is the velocity of person A after the separation? So they're standing together in the center of the ice rink, so they're not moving. So the momentum of the system initially is going to be 0. And this is equal to the momentum of the system afterward, m1 v1f plus m2 v2f. And I'm using 2 and 1 instead of A and B, same difference here. And we are trying to figure out the velocity of person A, we could say v1f, afterward. So let's move this over by subtraction, negative m2 v2f equals m1 v1f, and divide by m1 on both sides. Dividing by m1 gets rid of this m1 here, and we can cancel it, and v1f is equal to the expression negative m2 v2f over m1. And let's make sense of this real quick. If we take a look at what our numbers are, and we plug in here, we're going to end up having 40 in the numerator for the mass of the second object. We're going to have 7 meters per second for the velocity of the second object, all over 60, which is the mass of the first object, which equals v1f. This quantity turns out to be negative 4.7 meters per second. Well, this answer is completely logical. Let's go over it for 2 reasons. Reason number 1, the velocity of the first person after pushing off was positive 7, so this has to be negative right away, because they're moving in opposite directions to have equal and opposite momenta. Second, we'll notice that the mass of this person that moves at negative 4.7 is greater than the other mass. So the bigger person does not move as fast as the smaller person of 40 kilograms that is propelled offward at a higher speed. A pickup truck is carrying a 1,000 kilogram steel beam while cruising at a velocity of 25 meters per second. The beam falls out of the back of the truck, and it's still moving forward, but only now at a velocity of 18 meters per second. The truck suddenly accelerates to a velocity of 30 meters per second as a result of the beam falling out the back. From this, determine the mass of the truck. For a problem like this, we really need to identify what's going on here. So we've got the truck. Okay, here's the back of it. And we'll say that there's a beam in the back. I'll draw the beam in red. Now, as the truck moves forward with a velocity with the beam of 25 meters per second when they're together, Suddenly, this beam starts to slide out the back of the truck. So I guess it slides with a velocity of 7 meters per second backward, giving it an overall velocity of 18 meters per second when it exits the truck. So as soon as this beam falls out of the truck, it's moving at 18 meters per second now because it was moving at 25, but it slid backward at 7, so it's still moving forward because of inertia and the desire to remain in motion, but it's going to slow down once it starts hitting the ground and falling. But the key is to remember that the velocity of the beam after the collision or interaction or separation in this case is 18 meters per second. And that causes the truck to accelerate forward and moving it up to 30 meters per second. And this makes sense. If you have your foot on the pedal and you don't increase the force being applied, and suddenly a giant beam falls out the back of the truck, the car is going to start going much faster suddenly because there's much less mass to pull. So let's go ahead and list our givens. First, we have an initial velocity of the system, because they're together, of 25 meters per second. The initial mass of the system in the beginning is just the sum of the mass of the beam and the mass of the truck. The mass of the beam individually is known as 1,000 kilograms. The velocity of the beam after separation is 18 meters per second. The velocity of the truck after separation is 30 meters per second. So let's take a look at our equations of motion now. So before the separation, before any interaction, the masses are combined. So we have m1 plus m2, the beam and the truck, times the initial velocity of the system. But afterward, they're separate. So m1 v1f plus m2 v2f. Remember, the goal is to find the mass of the truck, m2. So the problem is that it occurs here and it occurs here. So one way to solve this problem is to go ahead and plug in all your numbers and then just simplify it by combining like terms. But we can still solve this algebraically. It's just a little bit messier. The easy way to solve this algebraically is to go ahead and start by distributing the vi over here to each of these two terms, yielding m1 vi plus m2 vi, still equaling m1 v1f plus m2 v2f. Now, we want to get m2 by itself, m2. So let's go ahead and move this m2 over here, and we'll go ahead and move this one over. We'll move this over by subtracting. So this side, we carry down the m1 vi from right here, but now we're going to move this over by subtraction. So minus m1 v1f. And at the same time, what we're going to do is we're going to keep this m2 v2f, but from that, we're going to move this over and subtract it. So it's going to be a minus m2 vi. And what this has done for us is it's allowed us to get m2 on one side of the equation, and we can then factor it out. So this becomes m2 v2f minus vi, equaling this same expression here. Now we're trying to find m2, so let's just divide by this quantity v2f minus vi. That gets rid of it over here because it's like a coefficient again. It's just a coefficient. So our solution for this problem, when we plug in, becomes 1,000 times the initial velocity of the system minus 1,000 times the velocity of the beam afterward, all over the velocity of the truck minus the velocity of the system initially, giving us a result of 1,400 kilograms. So the mass of the truck is 1,400 kilograms, and the mass of that beam was 1,000 kilograms, so it's a heavy beam that that truck was carrying. So we can see that there's a big jump in velocity when the beam was dropped from the truck. Your homework from this section is from 2 different pages here.